Hello, my name is Ryan Bay, and today I would like to go over thermochemistry within the AP Chemistry world, and specifically I would like for us to go over the basics of Hess's law, what exactly its applications are in the real world, and how to effectively use it in appropriate scenarios. So, beginning with Hess's law, I would like to give a brief definition of it. So, Hess's law actually states that the total energy within a chemical reaction is equivalent to its independent chemical reactions and their own respective energy outputs or energy changes. So this law is actually a variation to the first law of thermodynamics as well as the law of conservation. So why exactly do we use Hess's law, and what exactly is its significance? Well, Hess's law actually has a lot of applications, not only within thermodynamics, but also within many real-world situations and problems. Firstly, within the realm of thermodynamics, Hess's law actually helps with calorimetry, which allows us to assess different temperature changes within chemical reactions and analyze them. Within industrial processes, Hess's law is actually used to optimize energy outputs and enthalpy changes, as well as produce new materials. Within reaction mechanisms, it allows us to easily assess different steps of a reaction. And finally, we are able to calculate energy changes within thermodynamic calculations, which would be nigh impossible through direct experimentation. Here are some examples of real-world problems within Hess's law and how it could be used. To my left, you can see an image of fuel in which energy outputs are actually calculated by chemists and scientists in order to assess the effectiveness and sustainability of alternative energy sources, such as fuel. To my middle image here, you can see a photo of medicine in which chemical reactions and their enthalpy outcomes are actually analyzed and reviewed in order to see their scalability as well as their reaction conditions. And finally, different materials, such as this one here, which is ceramics, as well as composites and polymers, are tested through Hess's law with their physical properties in order to optimize their structures to make them more resistant to different environmental conditions. So these are just a few examples of Hess's law and its power in the real world. And as you can see, it is a very versatile and important law in our society. So now that I've gone over a brief overview of Hess's law and also some of its examples, I would like for us to have some general practice with Hess's law in order for us to essentially master this concept. So our first question here is a simple Hess's law conversion, which says use reactions A and B to determine the delta H, or the change in enthalpy, for the single displacement reaction. And as you can see, we have Cl2 plus 2HBr, yielding 2HCl and Br2. So what I usually like to do when I am exposed to questions involving Hess's law is that I would analyze what my products are within the reaction. So in this single displacement reaction, my products are the 2HCl and the Br2. And this is where our reactions A and B will come into play. So I'm trying to get my products on this side by using A and B. So if we look at A, it says that H2 plus Cl2 yields 2HCl. So I'm okay here because I have my products on the appropriate side, which means that I don't have to do anything to this reaction. However, on the other hand, we have reaction B, which says that H2 plus Br2 will yield 2HBr. So as you notice, the 2HBr is on the product side when it should be on the reactant side, and vice versa for the Br2 for reaction B. So in this scenario, what I can actually do is I can flip this reaction. So I will have reaction B listed down here like so. I can actually flip this, so the products would actually become the reactants. H2 plus Br2. Now that we have flipped our reaction, we must also flip our sign or negate our sign for delta H. So since we have negative 73 as our original delta H, we need to make the opposite sign, which is 73. And this is usually assigned in kilojoules, but it was not specifically written in this question. Just keep that in mind, it's assigned in kilojoules. And allow me to just simply rewrite the expression in equation A. 2HCl. That's the original. And since we did not manipulate that reaction in any way or form, we could just leave it like negative 185 kilojoules. Alright. And our end goal is to try matching up our two reactions, combining them, and synthesizing this reaction in the end. So, since we have H2s on both sides of the equation, we are able to actually cancel them out, kind of like in redox. And you would actually end up with Cl2 plus 2HBr will yield 2HCl plus Br2. And our last step here, now that we have our final equation, is to just calculate the sum of our delta H's. So if I just do a simple calculation here, our final answer will actually be negative 112 kilojoules. That is our final answer. Okay, now that we have done a simple Hess's law reaction, allow us to go into something a little more complicated, not anything too crazy, but instead of having two separate reactions, we actually have three here. So it says using the following data to calculate the enthalpy change, we need to find the overall enthalpy change of this formula right here. 3NO2 plus H2O yields 2HNO3 plus NO. So, as I mentioned before, look at our products. We have HNO3 and we also have NO. So, I notice I'll call these reactions before I even begin, X, Y, and Z respectively. You don't have to do this. You can do this as ABC, 1, 2, 3, whatever works with you. This is just my preference because I like using variables. So, in reaction Y, I can see we have 4 moles of HNO3 compared to the desired moles we want, which is 2 HNO3. So what we can actually do to manipulate this reaction Y here is that we can just actually divide it by 2. So that'll yield N2 plus 5 halves O2 plus H2O will yield 2HNO3. And since we divided our Y by 2, we must also divide our delta H by 2. So we'll be left with negative 128 kilojoules. Okay. I know that I said that we want to optimize getting our products on the right side, but I noticed that in reactions X and Z, we both have NOs. So what I would say with my next priority would be regarding matching the overall expression as described in green here, is that I would actually look for any reactants that I want to get on the left side as well. So in this case, in reaction X, we actually have 2 moles of NO2. So if we want to get this on, if we want to get the NO2 on the reactant side, what we can do is we can flip the sign. So my apologies, I will write it up above here. So 2NO2 will yield 2NO plus O2. That is only the first step. So first step, we must negate our delta H for X, but I also want to get the NO2 to have 3 moles. So what we can actually do is multiply the X by 3/2, which will give us the 3 moles. So if we multiply this whole expression by 3/2 right here, right? Our final equation for X, which I'll label as X prime, will be 3NO2 will yield 3 moles of NO plus 3/2 moles of O2. And because we multiplied our reaction by 3/2, we must do the same for 116, which is the same as 1.5. If I do this calculation here, it will result in 174 kilojoules. So let me just write that down here. Okay, and now that just leaves us with reaction Z. Okay, so my final reaction, I want to have 1 mole of NO. And since on the reaction side, I have 2 moles of NO, I would want to optimally get this to the left side and reverse this reaction so that I will end up being left with 1 mole at the end, because I have 3 here, and if I just subtract on the reactant side, I'll be left with 1. So I will reverse this equation, so it will be 2NO will yield us N2 plus O2. Okay, and our delta H, since we flipped the reaction, will be left with negative 183 kilojoules. Okay. And now we need to get this green reaction here, the overall reaction, to be the same as these 3 reactions combined. So let's work with what we have. So we have the 3NO2. I'll actually use a different color for this. We have 3NO2. That's good. So 3NO2. And then we have our H2O right here, plus H2O yields us the 2HNO3, which we have right here, and then it should be plus NO. So it looks a little complicated from this angle here, but allow us to make a few simple calculations. So on our reactant side and our product side, we have N2, so we're able to cross those out. And also for our oxygens, we have 5/2 oxygen, but we have 3/2 oxygen and 1 mole of oxygen as the products. And you should know that 1 oxygen or 1 mole of oxygen is 2/2, so that'll actually just end up being 5O2. And this will actually just cancel out with the reactant. And finally, since we have 2 moles of NO on the reactant side, the 3 moles of NO on the product side will be left with 1 mole of NO, giving us the whole equation complete here as mentioned in green. And our final step into solving this question is to just simply calculate the delta H's. Calculate their sum, and if you do this correctly, you should be left with negative 137 kilojoules.